This example problem on slide 25 is an example of basically how to calculate a pH change in a buffer solution after adding either an acid or a base. The purpose of a buffer is to basically minimize the amount of a pH change that takes place after adding an acid or a base. And so we're going to introduce a new type of chart to help us solve this type of problem called a before and after chart. So this is example problem on slide 25 of our chapter 18 PowerPoint, and the question states a 1 liter buffer solution contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate, which is our buffer solution. The value of Ka for acetic acid is 1.8 times 10 to the negative 5, and it wants us to calculate the new pH after we add 0.01 moles of solid sodium hydroxide to the buffer. So the first thing you need to do when setting up this type of calculation in order to basically solve for our new pH after adding, in this case, base to a buffer, is to write an equation for what's taking place in solution. So since in this case we are adding a base and it's got hydroxide, we're basically going to be reacting our acid with a base to produce water and then our conjugate base. So the equation you're going to write, that's the first thing you need to do, figure out your equation, is going to be OH minus, that's our base from sodium hydroxide, plus our acetic acid, that's one of our buffer components. You're going to react. All we're doing is transferring a proton, our Bronsted-Lowry type equation, where acetic acid is going to act as an acid, give up its proton to hydroxide to form water and the acetate ion. So now that we know what's going on in solution, we've written our equation, now we can set up our before and after chart. So it's very similar to a rice chart. You have a reaction, and then you're going to have a before addition change. We're going to represent that with a triangle. That's after addition. And then A for after we add. So you're going to have 3 parts to this: before addition, the addition amount, and after addition. And that's your before and after chart. Now the key thing for this chart, and we're going to use this type of chart throughout this chapter for particularly performing calculations with titrations, it is that amounts, if I could get my PowerPoint to work, must be in moles, not molarity. So this problem is nice because they've already given us moles of our acid, moles of our conjugate base, as well as moles of base we're adding. So my before portion is going to be just what's stated in the problem. So for OH minus, that's going to be my 0.010 moles. For my acid, it states in the problem 0.100 moles. Water we're not going to include because it's a liquid. And for our acetate ion, that comes from the 0.100 moles of sodium acetate. So now it's similar to a rice chart, but slightly different. We have to look and see what our change is going to be. And so we look at this and figure out what our smallest mole amount is. And that happens to be our base. And that's what we either add or subtract from everything. That's going to be our change. So since our reaction is proceeding in the forward direction, our two reactants, OH and acetic acid, we're going to be subtracting this amount from, and for our acetate ion on the other side, we're going to be adding the amount. So remember to determine what you're adding or subtracting. It's the thing that's there in the smallest amount, which happens to be our OH minus. So for reactants, we are going to subtract that amount from it. And for our products, we're going to add that amount. So then you're left, and if you want, you can draw a line here. It's kind of like our equilibrium portion if we're comparing to a rice chart. Your OH, if you subtract something from itself in the same amount, that's going to be 0. For our acetic acid, 0.1 moles minus 0.01 happens to be 0.090 moles. And for our acetate ion, 0.1 mole plus 0.01 mole is 0.110 moles. Now that we have basically how our moles have been modified by the addition of our base, sodium hydroxide, we're going to use these to calculate molarity so that we can eventually calculate pH. So in my problem, it states that I have a 1 liter buffer solution and that I added sodium hydroxide as a solid. So that means my volume hasn't changed. So I'm currently in units of moles. I want to be in units of molarity, and we know molarity is moles over liters. So I'm going to divide both of my mole amounts that I have by 1 liter. Oops, not liter, 1 liter. And that 1 liter comes from the fact that in the problem it states that I have a 1 liter buffer solution. So obviously for both of these, my molarity is going to be the same as my mole amount since it's just a 1 liter solution. But that's not always going to be the case. So now I have two components. I have my acid and my conjugate base, and I'm going to use both of these amounts to figure out my new pH of my buffer. So one way we could go about this is by doing the whole long rice chart calculation, but we just learned about in the previous example that we worked together, the Henderson-Hasselbalch equation, which says that pH equals pKa plus log of my, we can say, A minus over HA, or A minus is my base over HA, which is my acid. So I currently have molarity for my acid, molarity for my conjugate base, and in the problem it also gives us our Ka 1.8 times 10 to the negative 5. So now all that's left for this problem is to plug all my numbers into this Henderson-Hasselbalch equation to calculate my new pH. So pH is going to be negative log of my Ka, because that's what pKa represents, and Ka is 1.8 times 10 to the negative 5, stated in our problem, plus the log of my base, or conjugate base, 0.110 mole, molarity, sorry, not mole, over 0.090 molarity. And so if you do negative log of our Ka, you get 4.74. If you do log of those two items over each other, you get 0.087. And if you add those two together, you get that the new pH is 4.83. So that is how to perform a calculation wherein we're adding something to a buffer to disturb its equilibrium. And this will come back again when we start looking at titration calculations.